Hi everyone, thanks for coming. It's my pleasure to present today Camila Fernández. Camila is researcher at the CNRS in France and professor at the UDEC in Chile. Camila holds a PhD in marine biogeochemistry, and her research focuses on understanding ocean processes and their vulnerability to global change, mostly by linking biogeochemistry with microorganisms. Camila has outstanding leadership skills. She leads the COPAS Coastal Center, a research center of excellence in Chile, which studies the oceans. She also co-chairs the Scientific Advisory Committee on Climate Change for the Ministry of Environment in Chile, and is member of the International Network of Climate Advisory Councils. Camila has participated in numerous national and international projects, such as the Tara Microbiomes Expedition, and among many other things, she is member of the Women's Network of Microbiology in Chile. By having said that, please an applause for Camila.
Am I on? Yeah? Thank you. Thank you. I turn it on. Off. Yes, it's okay. So thank you, Mireia, and thank you everyone for being here. I know it's kind of a tricky day because you're in the middle of a storm. So thank you for taking the time to listen to this talk, and thank you everyone at home, the comfy. It's a pleasure for me to be here today. I know Mireia since her days in Chile, and it's been a pleasure collaborating with her. And it's an outstanding community that you have here, an outstanding building, a lot of history going on. So it's a privilege, really, to be here. So my interest today is to talk about extremes, which is something that in the international scientific community is getting more and more common, right? But really, well, that's me. That's the less fun part. But just to make sure that you know what I do, we're going to talk about biogeochemistry today, which is a mixture of how the physics and the chemistry of the ocean modules what happens to biology. Or the other way around. That's a way to also put it. That's my main research area, but over the years, I've been migrating towards global change in the sense of making sure to understand how environmental stressors define what happens in the ocean. So I've been interested in UV radiation, the ozone layer, what happens to temperature, what happens to oxygen, what happens to many other things, but always focusing on microbes. You won't hear from me a lot of diversity today. I won't be showing those OTUs or really sequencing exercises, which I use, but mostly you will hear from what they do. So for me, as a biogeochemist, the main issue is to see the ocean like this, as a mixture of interactions between functional groups that ensure the main ecosystem services of coastal oceans around the world. But we hear from them for what they do. So I search for functions and regulation of these functions in the ocean. That interest was recently consolidated in the international community by the Plankton Manifesto, which is not other thing than an effort of many, many scientists around the world to put forward these tiny microbes that live in the ocean at a density at around 1 million cells per drop of water, and that are responsible for everything that happens really in the ocean. So they can provide services, they can provide a lot of things and a lot of answers to climate change and the effort of mitigation and adaptation. And for that, we launched this call for opportunities that can arise through the study and the valorization of plankton. So we can talk about that after the talk if you want. But for today, we're going to talk about extremes. So what are they, really? What is an extreme event? why should we be concerned about them? Are they happening really? And what kind of extremes can we expect from climate change? What does it mean to study them, and why we choose to do so in remote areas? And most importantly, today, at this stage of my career, having gone through a lot of different kinds of projects, it's very important to transfer what we know to society. So a lot of my research and a lot of my efforts as a director of teams, back in Chile and in France, is to go back to society and deliver what you know. The form of which is very important to define also as well. So we're going to talk a lot about that today. But extreme events. So this is a picture of the world with a little cartoons that symbolize different kinds of extreme events. And what we call extreme event is just a matter of an operational definition. What is an extreme event really? It's something that doesn't happen really often in a certain place at a certain time with a certain intensity. What is extreme for, let's say, Concepción, Chile, might not be an extreme in Colorado, United States. A tornado, for instance, is something that happens once every 100 years, where I'm heading in Concepción, in Chile. But it happens really often in certain places in the United States, for example. So an extreme for me will not be an extreme for them, right? On the other hand, on the scale of the intensity and the frequency of the events, any modification of a certain pattern or a constant pattern of events can be defined as an extreme. So we have all kinds of streams, and we did a little exercise a while ago with some colleagues to define what is really, an extreme event. It can be a major bloom out of time. It can be a major storm. It can be a marine heat wave. It can be an atmospheric heat wave. It can be a combination of both. But what you see in this map, really, apart from the different definitions or the different kinds of extreme events, is the absence of icons in most of the most iconic parts of the ocean. For instance, there's nothing here, there's nothing here, nothing here, and a lot of things where most of the scientific activity is going on right now. So the same is true for, let's say, the IPCC reports. The representation of the southern hemisphere, a certain part of the ocean, is less than what we could expect. So it doesn't mean that there is not extreme events going on in those parts of the ocean. It's just that we don't have the data to prove it, or that we are not looking constantly enough, hard enough. So an extreme event is related to tipping points. We often say that extreme events are more frequent and more intense because we are heading towards stable status on the ocean that are different to what we knew before. And for that, it's important to check the definition of a tipping point. A tipping point is where you come from a stable status of any kind that you know and you can actually define and predict. Slowly modifying the environment, you will go towards a different state. And the tipping point, when it's crossed, has one single characteristic, is there is no turning back. So today, we have defined at least 25 tipping points across the world that are characterized, defined, and studied. Yeah? The problem with that is that it's very difficult to know what happens next. So there's the usual melting glaciers and such in the northern hemisphere, changes in the circulation of the ocean, changes in the patterns of El Niño, these warm events that oscillate between warm and cold with El Niño and La Niña, and that has very much an influence into the fisheries of the world and the habitability of the coast of South America. But the problem is that we don't know really what happens next. So we cross one stable state to go to another stable state, and then what? Then we have to start over collecting data to predict what's going to happen next. So it's kind of a different reality. And right now we have 25 different realities that need to be described and modeled forward into the future. Because what we know back is no longer, correct. So the point between this reality and extreme events is they are very much linked. The fact that we are changing the steady state of a lot of ecosystems means that this kind of extreme, out-of-scale events like phytoplankton blooms that can be toxic or not, but they're out of scale, floods, marine heat waves are becoming the new reality in most of these areas. And my problem as a scientist that work in the East Pacific Ocean is that there's nothing here, but it doesn't mean that we haven't crossed a certain tipping point. So a lot of what I'm going to show you today is oriented towards that kind of challenge, to go look for the tipping points ongoing or that are imminent in remote areas where we really don't have much data. So for climate change in the ocean, really we focus on three major threats. It's getting warmer, it's losing oxygen, and it's getting more acidic. We all know what that means, and that they are deeply interconnected, and one is really not separated from the other. Because the ocean is really salty water, if you warm it up, you're going to lose the solubility of gases and such, and that changes, evidently, the chemistry of the, in which most of the microbes and most of the species inhabit. So focusing on these parameters, the pH, the oxygen, and the temperature of the ocean, already, if we are talking about extreme, we can identify at least two, or three kinds of extreme events: marine heat waves, atmospheric rivers, and deoxygenation of the ocean. And today, I'm going to talk about just the first two. This is a composite that shows thermal variability in southern Chile. So this is the coast of Chile. And we are here in the frontier with Peru, and we are headed towards Patagonia. This is northern Patagonia. As you know, Chile and South America is it's kind of a funny country, because it's very long, very narrow, and it has everything in it. So if you're going from the north to the south, you're going to start very hot in the desert of Atacama with a lot of minerals, resources, so you have no problem in the mineral department for phytoplankton and for the coupling between the terrestrial environment and the ocean that is just beside. The problem is that, along with Peru, they share an oxygen minimum zone that is very emblematic. The waters here between 50 meters and 300 meters has no oxygen. And that has a lot of explanations, which are physical explanations, but also biological explanations, one of which is the fact that Peru and Chile sustain 10% of the fisheries in the world, and all that organic matter needs to be respired somehow. So if you're going to produce all that organic matter, you need to consume a lot of oxygen and a lot of energy to just destroy it, as it is. And that consumes a lot of oxygen. If you combine that with the fact that these coasts receive the oldest waters in the world, then you have a combination of factors that means that this is a unique environment to be studied. So you have that in the south, in the north, and then heading south, you start to have, a lot more green, a lot more rain, a lot more humidity, but also glaciers. And we have the second largest reserve of glaciers and ice, in the continent, in the world. So both of those factors combine in making this a natural environment. What has that to do with temperature? Well, the evolution of temperature in the sea surface in Chile is telling us that climate change is arriving to those waters as well. And we see more cold events in central southern Chile, central northern Chile, because of the change in the wind patterns. The anticyclone of the Pacific is moving southward, so it's changing the way the water is moving along the coast. So we have cold events in the waters in the north and warmer in Patagonia. Naturally, you would think glaciers and desert, but it should be the other way around. But no, we have, an inversion of trends that we are seeing, combined with the fact that here you have the frequency of marine heat waves. Marine heat waves are really tricky to detect because you need to have certain conditions. It needs to be above half a degree, at least, in the water for a certain period of time. So a warm event should be of more than a week. If it's 3 days, it's just a warm event, but it's not a marine heat wave. We have detected in frequency at least 3 marine heat waves per year in most of the country, with an intensity that is really way above half a degree. And the maximum duration of the marine heat wave that we have detected by just looking at the statistics and looking at the data and trying to using artificial intelligence to detect those kind of event a posteriori, 90 days of duration, which means that the water, even though it's cold, because it never surpasses like 20 degrees Celsius, which is not what you expect in the Mediterranean, for instance, even though it's 20 degrees or 19 degrees, it is above the average that it should be for more than 3 months in a row. So what does it mean for a functional group of microbes to be above the average for that long a period of time? You would think that half a degree is not that much, but it means a lot in terms of the trophic status. For an ecosystem such as this to be functioning, you need 3 things. You need energy, you need nutrients, and you need turbulence, which means that you ventilate. You need to be able to breathe, be able to feed, and have the energy to do both of those things. Marine heat waves subtract the turbulence aspect because warm water is more stable. Also, you get away the nutrients, take away the nutrients because more stable water means that you run on recycling and not really on new sources of nutrients. And then you just have the energy. And that is not a sign of a healthy ecosystem. So marine heat waves mean that you stabilize your water column and you deprive it more or less of at least 1 or 2 sources of nutrients. So it's concerning. So we took on the task of measuring things, during a marine heat wave. First, we needed to identify them, so be able to catch them. Then, using predictive models, we can know when a marine heat wave is going to hit, at least an atmospheric one. And then we can say, well, if it is a coupling, maybe we will have a marine heat wave or a marine warm event. And if you have one, then you can go to the field, sample it, and measure something. What we did here is to take samples over a 4-day period of time when we knew that warming events were going on. And we measured 2 parameters that have to do with what phytoplankton does with nutrients. So phytoplankton to grow needs same things that we do. You need carbon, nitrogen, phosphorus, nutrients in general. So we measure the amount of carbon and the amount of nitrogen that they use to be able to say how fast they are growing and what the effect of a marine heat wave could be. So during the heat spike, we actually saw that primary production was a little bit up. So you could say, well, yeah, okay, it's not a really super, different response. But what we did see is that during the course of the day, there is a high frequency response. So depending on how hot it gets, microbes will respond very quickly, which is something that we already saw with bacteria. That is bacteria that can recycle nutrients. They are really very fast at responding to solar radiation and temperature. So they will select, in situ what groups can adapt faster to these conditions and ensure the function to continue to happen. So the message here is that the amount of ammonium, let's say, which is the first thing that you get when you put organic matter into the environment and you let it just perish, be destroyed, the first thing that you obtain is ammonium. So it's the first sign of recycling, really, in the ocean. Everything that happens there, any bloom, any cell, any fish that dies, transform almost immediately in tiny particles of organic nitrogen and carbon, and then immediately after that, ammonium. So it's really what makes the ocean run. And the rates go up by small groups of microbes when the warm conditions ensure. So big diatoms, big phytoplankton, not very happy, small phytoplankton and small bacteria, really, really happy, and the system starts functioning based on recycling and not really, getting new sources of nitrogen. Another thing that interests us in these kind of extreme events is atmospheric rivers. What you see here is the other end of the scale is a lot of rain in a very small period of time. So a little bit like what you had these past few days. It's been a month of rain here in Madrid. But if you remember a while ago, there was a lot of rain in Valencia, a lot of flooding, a lot of things. And that was related on a certain kind of storm. Well, these storms are really common globally. But they are characterized by really being these gigantic tubes of water that travel across the Atlantic or the Pacific and hit the continents in 2 ways. This is the Cordillera de los Andes. This is South America, right? This is Brazil, Argentina, Chile. You almost don't see it because it's so narrow. But that is the topography. And atmospheric rivers can be of 2 kinds. Either it crosses the Pacific Ocean and hit head-on, and therefore will cross the Cordillera and go straight to Brazil, or it will hit a little bit north and travel across the country. Right now in Chile, per year, we are being hit by at least 5 or 6 of these events between winter and spring. So now we are entering the season where this will start happening more frequently. It means that it can rain above 90 millimeters in the space of 3 or 4 days, which is a lot. A normal event of rain can be 15, 20 millimeters. A huge amount of rain could be 50 millimeters per day, but we're getting like 100, 110, 120. So that's a huge amount of water in a very short amount of time. So it leads to eventually flooding and socioeconomic losses and problems of that kind. So what happens with these events? What happens when it rains a lot? And if you could actually check on the latest that has happened this year and the year and last year in terms of publication, and you realize that a lot of things happen with an atmospheric river. It's been related recently to the consequences of earthquakes, for instance, because of landslides. So you have an earthquake, and immediately after, an atmospheric river, and the combination of both means that you need to prepare for those kind of combinations. The message here is that marine heat waves, atmospheric rivers, earthquake, and such and such and such, in this uncertain new stable state in which we are, needs to be considered as a combination of multifactorial risks. And that is the message of the colleagues that in this paper. More in the ocean part, atmospheric rivers has been relating to an increase, depending on the type of atmospheric river, you can increase or decrease upwelling, which is the fact that the wind gets to the continent in all the EBUs, the eastern boundary currents in the world, like California, South America, Africa, you get the same pattern. The wind gets the deep water to the surface and fertilizes the ocean. That's coastal upwelling 101, right? Well, this is the main reason why these coasts, Mauritania, South America, California, is so rich. You know? There's so many fishes in there, and so many phytoplankton, and so many carbon fixation in primary production. And therefore, why those points are where most of the CO2 of the atmosphere gets into the ocean. The ocean as a whole absorbs more or less 27% of anthropogenic carbon every year. And most of that 27% happens in those areas because they are very active and very windy. So a lot of wind, a lot of upwelling. Well, atmospheric rivers, because of the atmospheric pattern that prevails during those events, can lead to either increased upwelling or increased downwelling, which is the opposite of what we expect. So when a storm hits, you can have, depending on the orientation, if it crosses the Cordillera or not, you will have an increase in deepening of water, which means that you will have just burying a certain amount of water in deeper layers instead of going up. So that means that the biological engine that drives productivity in the Pacific Ocean kind of depends on the occurrence of these kind of events, which wasn't the case before, okay? Or at least we didn't notice. So certain consequences can have immediate effect in the functioning of marine environments. For me, in particular, rain means microbes, right? So I study microbes based on what they do, right? So my question was, so what is in the rain? What can you find in the rain? And the first thing that I did was to collect rain a lot, and put in that in a little flask, get some vitamins in, and see what grew. And it turned green, very quickly. So my first observation was, there's life, When you think about rain, because of what they teach us in school, the cycle of water, right? So everybody at school gets the cycle of water. You have evaporation that goes to the clouds, then goes to the snow, right, the river, and back to the ocean, right? So that's the little cycle. And it's true, that's the cycle of water, one-on-one. But that makes us think about it as kind of distilled water, right? If you think about rain, you think about something inert, So it's water, but it doesn't have to have anything in it because it's right connected to the snow, and you don't drink snow because it doesn't have any electrolytes, so there should be nothing in the rain, right? It's kind of something that is in our minds just because of what we learn in school. It turns out it isn't, and I was asking the question, so what's in there really? What's in the rain? But there's a lot of things in rain. There's a lot of microbes, there's a lot of nutrients, there's a lot of contaminants, there's plastic in the rain, there are persistent organic compounds in the rain, and there is the potential of creating microblooms in the rain. It's been frequently described events of high primary production, phytoplankton blooms, right after a storm. The thing is that it's not very common for you to go to the field after a storm because the very existence of the storm prevents you from going to the boat and in the field and taking samples. But satellites show that right after a storm, depending on where you are, you can actually have a little bloom. And my question was, why? Is it because of the wind and the very characteristic of the ocean you're studying? Or is it because of or is it because of the rain and what it takes? So what's the relationship there? So we took to Patagonia. This is Caleta Tortel. It's really the end of the line in Carretera Austral. You can't get south than that by truck. It's a 24-hour from the middle of Chile where we work. Is kind of a 24-hour trip to get there. So it's really remote. In the 90s, it was accessible only by plane, little plane, and by boat. And today, it really depends on boats to do the connection with the continent. But it's one of the most pristine areas in Patagonia to work. This is a fjord of Caleta Tortel with the classic, glacier water on top and marine water above. So we took, this is our little ship, Sur Austral. So we took to the field to try to get one of these events, which are very common now in Patagonia, and sample it. This is another view. This is our lab in Caleta Tortel. So not very easy to work in this condition, but always a super good experience. So you need environmental variables. You need to go to the water to do profiling. You need samples of rainwater and such. You need a meteorological station, which is there, and it's not easy to get there to change the batteries, but we do it anyway. But that means that extreme science, is kind of a reality for us. If you want to get the answers in the most remote areas of the planet, you need to be ready to get dirty and get to the field and get the materials in and put the effort. And that's related to what I'm going to talk about later, and that's the connection with the local community. So you need help to do all this, right? But so Caleta Tortel is here, right in the middle of both ice fields, north and south. It's the last really remaining reserve of glaciers in the southern hemisphere, apart from Antarctica. And we are right in the middle of it. So temperatures are very low, of course, and it's a very stable water column. But during the space of, in winter, for instance, where we have these events going, you can have a little bit of chlorophyll going, and disappearing very quickly. So we took measurements of rainwater and compared it with regular water from the surface in the fjord. And actually, when you compare the blue, which is the fjord, with the red, which is the rain, there were some differences in what you receive. So what happens when it rains is that the water that comes with certain characteristics would mix immediately with the surface of the fjord, which has a lot of silicate. So this is glacier water, the fjord, which means that it has no nitrate, no phosphate, no nothing except a lot of silicate, which is fundamental for phytoplankton to grow. It's like the thing that makes phytoplankton diatoms grow and absorb CO2 from the ocean. But if you don't have the rest of the nutrients, you can't do anything with that silicate. Well, there comes the rain, because the rain is loaded in ammonium, and is loaded also in phosphate and nitrate. It's loaded in organic nitrogen, which is like the donut for any microbe. If you're a microbe in the ocean, running around trying to get your nitrogen, if you see this and you see that, see ammonium and DON, you will immediately go and get it because it's the easiest way to get your happiness, right? So a lot of nutrients come in the rain. We did the exercise of check if that nutrient will actually go in the cells and be used. And the answer is yes. When you mix the water from the rain with the recipient water in the fjord, you get a boost of primary production immediately. So instead of being inert water that comes and just deposits itself in the ocean, the rain has a fertilizing effect. And you can see that by measuring the basic chemistry of the ocean. So atmospheric rivers had a real biogeochemical effect, a real impact. It doesn't really only impact the way we transport ourselves, because we get all flooded and such, but it will also modify momentarily the trophic status of the ocean, creating microblooms in one case or preventing it from happening on the other. That explains some things, and in this really complicated slide, I don't want you to check on anything other than this little arrow there, which means that in Patagonia, what we see is that there are kind of two regimes. One that has in the north of Patagonia, where you can actually get more wind and more mixing events, that we get more nitrate into the water column, and the other one where we are, where ammonium and regeneration, recycling of the organic matter that is already there, gets the engine going. And so what we saw with atmospheric rivers makes sense to understand this kind of observation. And we are starting to put the puzzle together to get a better vision of what the future of Patagonia will be. Like, it's no longer an ecosystem where winds prevail and the raging sea will provide the nutrients from the deep. But it's getting warmer and will go on recycling, most likely, which is not a very good news for atmospheric CO2. Because for you to count atmospheric CO2 going into the ocean, it needs to be other than recycling. It can be recycling, it needs to be new. So you need wind to ensure the climatic role of the ocean. So, yeah, by observing and checking on the microbes that do these kind of things, we can have a better understanding of our ecosystem. And what we did is actually put in those remote areas as much equipment as we could and leave it there for them to get our time series on diversity of phytoplankton and also chemistry and physics. And we get something like this, that we can check from Concepción or from wherever we are. But all this is super good because we publish it and we have a better understanding of what's going on in Patagonia right now and what will happen in the future with this extreme event. But as I said before, in this time at this point, what you need to do with all this information is get it out there. You know? Get society informed and get the latest evidence into the table of what people are trying to make decisions about climate change. So that's why we get involved in things like the Council for Climate Change for the Ministry of such, or the International Network of Councils for such and such, because it's really important that people making decisions have the latest evidence in the table. And the evidence is accumulating fast, and it's really changing very quickly. So it needs to be a constant exercise. But most important of all, general public needs to be informed as well. But really, really informed, not really alarmed by this, but get the evidence, out there, get the data out there. But how do you do it? You can sell it as, I'm an extreme scientist working in an extreme environment, and I'm here to teach you what I've learned of my experience, like Indiana Jones, right? But it doesn't work that way because of expectations. We function in this kind of the spectrum, but most of the general public functions in that kind of a spectrum. The same thing can be regarded as in many different ways, and it's a matter of dialogue. It's a matter of language. We don't speak in the same language, and we don't see the same thing in the same place. So it's very difficult to reconcile both visions. It's like getting that effect in a school or during a talk, or getting that effect. How do you get from this to that? Well, and how do you get from this to that in this kind of environment, which is Caleta Tortel, just for the pleasure of the eye, right? This is morning in Caleta Tortel. Nothing happens there, really. Everything is very peaceful. It's a very small community, but it's fundamental for them to understand what's going on because they are going to experience the effects of climate change firsthand before us. So people in Bangladesh, for instance, need to understand what's going on with the flooding way before people, let's say, in Australia. So local reality is really important. And we spend a lot of time thinking about the best way to make people not only understand the impacts of climate change, but take measures to adapt, to prevent, to mitigate, or even to adjust to reality. So it all starts with going to the schools and the regular thing that everybody does. But there's three things that are true when you talk about transfer of knowledge. You can teach somebody, you can talk to somebody about what you do, and that's outreach. You can teach somebody to do something that you know how to do, and that's transfer of knowledge. Two very different things. But the truth is that people will protect what they love, and they can only love what they know. So you love what you know, and you protect what you love. So you need to appropriate scientific knowledge somehow. So because we spent 14 years in Caleta Tortel working, we were kind of part of the community, so we decided to do something else. To combine the vision that the local community has on the surroundings with all the scientific information that we had and we didn't know how to explain. And the result was a common project with the local community to build an open-air museum, a scientific open-air museum for the people of Tortel, by the people of Tortel, and with a local impact in circular economy, because we were boosting as well. The objective was to boost local tourism, sustainable tourism. We wanted tourists in Caleta Tortel to stay one more day to boost local communities, but at the same time, to get the latest scientific information out there. So that was a challenge, and it translated in the construction of this museum. Fun fact about Tortel, there's no roads, there's only passerelles. You can't, there's no elevator, there's no, there's only stairs and passerelle because it's really a village built in the fjord. So we needed to do the museum in another passerelle that we had to build for that. This is how it looked like, during the construction. And during the construction and during the development of the project, the design of it, or the contents, were made with the community. So it was important for them that the local culture was present, the history was present, the local art was present, and so it was important for us too. But for us, it was important to include glaciers, include climate change, include risk of flooding, include biodiversity, include terrestrial and marine coupling, include what's a fjord, where are you right now, and where will you be in 20 years' time. And it was important also to include how to adapt. So this museum was inaugurated in January 2024. So far, we've covered like 56 countries, and in 2 summer seasons, we accumulated like 4,000 people. We are very happy with the result, and so are the people of Tortel. This museum is full part of the touristic circuits of the whole region of Aysén, and we are expanding now to make of this a protocol that you can apply to anywhere in the world. So how to approach scientific information, local and cultural background, mix it, and make it something that people can appropriate. So this doesn't belong to the University of Concepción as much as it belongs to Caleta Tortel. People appropriate this information, and they are now talking of climate change like they own the concept, and how they can adapt locally to what's coming. Our responsibility is to ensure the update of the information. So everything that's there needs to be updated with the latest scientific information. And let's remember that they live like 2,000 and something kilometers from the capital of Chile. So for them to get the latest in this format means that 56 countries every summer can have it as well. So it's a major change in the way that we see transfer of knowledge. So when you're here doing this kind of project, you cannot go back to just be content to go into the school and do the seminar. We need to go forward to the other end of the transfer scale. This, for us, was the major challenge in last year's activities of the center that I ran in Chile. And it will undoubtedly be the next major challenge in whatever region we decide to do this next. For that, we have an array of observation along the entire country, so we can choose where to go next to make the integration of what we know and translate it into a cultural dialogue about climate change with local communities. And this is the team. So thank you very much, and thank you for your attention.
Thank you very much, Camila. Now it's time for questions. If anybody in the public has any question, please. Carlos.
As I understand, the rain in southern Chile comes from the Pacific. So do we know where does the ammonium come from?
Well, there's a lot of organic contaminants and organic compounds that come with the rain. And so rain is funny because there's the composition of where the rain is when it's actually in the cloud is very different to the one that you get, at the soil or whatever. So it's a dirty substrate to work with. The thing is that water, with elevation, has a certain composition, and you will have very high in the stratus, atmospherically, organic compounds, plastics, microbes, and such that are actually dying and being recycled. But as it descends, it absorbs a lot of things. So what we need to do is to get a plane and sample, and then go for layers. We know that rain in the city is 10 times more dirty than the rain in Tortel, because you know what you get, but in the city it's really dirty. So if you have an umbrella, please use it. But it comes mainly from organic matter, being recycled in situ.
Thank you very much. Any other question?
Well, thanks for the talk. So you showed 25 tipping points in this map that you showed.
Yeah.
Do you know how these places are defined? So is it something qualitative or is there something quantitative? Or
well, it
where
is.
You locate this?
Yeah, it is quantitatively because what we do is that internationally, you get modeling exercises to tell you what the predictions are. And once the frequency or the intensity of these variations prevent the system from going back, then you can declare a tipping point. Well, for instance, for Greenland and for the ice cape, once you get an open space, in summer in the Arctic, then it's very difficult to go back to the way it was 20, 30 years ago. So if your predictions are that there is no way we get to, like the 1.5 or 2, it's almost certain now, we cannot say it for sure, but it's almost certain that we will pass the 1.5 global temperature rise. It's like a 99% sure. But we cannot say it, right now. But it's very probable. So it's that kind of exercise. It is the same way for El Niño, for instance. We are seeing less very, very big events far away in time, but more frequent, shorter, and very intense events. So that's a different pattern altogether that we had 30 years ago. It's merely by comparison, right, and statistics.
Thank you so much for the talk, and congrats for the great effort doing this work with the local community. My question is not so much scientific, it's related about this transferred knowledge. I wonder, because scientists, many times we pay attention to the details, and nowadays our messages are trying to be simplified, so to say, so people can get the important information, but that's becoming a problem, I will say, sometimes, since we say it's going to be warmer, but then in some areas it's colder, or for example in Spain it's going to get drier in general, there's the idea, and then suddenly we are having the wettest March in history. And people at the end are starting to mistrust science. And I think you mentioned that we are in this moment that we are changing the steady state, and information is sometimes contradictory. It's not contradictory, but the way that people feel is contradictory. How do you fight against that? Because people wants to get simpler facts, and simplicity sometimes is complicated to deliver.
That's a very complicated exercise.
I mean, this is not a question. How do you do with the local community? Because I think as well some people don't want to hear what scientists know, or even we are failing, and when we fail, it sounds like science is failing in general.
Yeah, you can look at it like that, or see it as an opportunity. Well, the fact is that there's a language problem here. So when, let's say, somebody wants a solution, and because, I don't know, we need to improve our sewer system, let's say, for receiving all this rain. I need a solution. Let's go to the scientists, the local scientists, and ask the question. Our response as a scientist will be, yeah, but I don't want to, pretend that I know what I don't know, and I don't want to make promises that I don't know for sure I can deliver, and I don't want it to fail, because then, and we are very busy, having that kind of thought, while the person looking for the solution is already out there, talking to somebody else, and getting a solution that is not based on science. So what we did was not ask al olmo que te dé peras, and get some intermediate players in place. So you don't need to do everything. Scientists don't need to talk, another language, but you need somebody that understands both worlds and can make the connection. The other thing is that data talks by itself, and you need to let the data talk as well. So you need to, there's interpretation of the data, perfect, but the data is the data, yeah. And what we do with policymakers and with when we talk to the ministry, for instance, of the environment, to say, well, this is what the data is showing, but are you sure? I'm as sure as the data is telling me to be, They don't like it, but it's an exercise that needs time to be perfected. The muscle of the transfer of knowledge is not something that comes with academia. It's really the opposite. So it takes these intermediate players, which more often are engineers that work in technology, or engineers that work in project management, to do this connection. And when the connection is done, then you can talk your own language and get the solution. The key factor also is time. Timing, and get the time to gather the sufficient information. You don't rush these kind of things, but once you get the right connection, it's very good to take the time to prove the solution locally. And that word local is very important as well, because the response to climate change that Madrid will have compared to Barcelona, where I was yesterday, is not really the same. So priorities need to be based on local reality and not, centralized climate policies, which is something that, fortunately, in Chile is really taking on, with every region having its own adaptation program. So that's very important as well. But it takes a lot of time. I mean, it took us 20 years to get here. So if you start now, in 20 years you will be super, but it's urgent to do so.
Thank you, Camila. More questions?
Thank you for your talk, very inspiring and interesting. I was wondering if the rain rivers that you mentioned in your talk are somehow related to ocean currents, like the thermaline currents and so on?
Oh, that's interesting. No, no, yes. Everything is related, right? These are atmospheric events that have direct effect on how the ocean is moving. So if you can provoke enhanced downwelling events, then it means that you are actually affecting the currents. It's not the other way around. On the other hand, ocean currents prevent you from having heat waves, real 40 degrees heat wave in the ocean. And one of the problems we have is that we are kind of slowing down some of them. So the ventilation system is failing a little bit in some areas. But the fact that, and I kid you not, I mean, 5 years ago, 10 years ago, the relationship between atmospheric events and the surface of the ocean was not even an issue for us. And the fact that the word ocean came into the negotiation of climate change like in 2021, or 2019, is reflection of the way, the compartmentalized way that we see the whole ecosystem. So part of this RAIN project is to start looking at the whole water cycle as a whole. And when we talk about carbon, we need to see it as a whole. So there is a relation between ocean and the atmosphere.
Maybe because also related to the temperature?
Maybe because related to the temperature. We are seeing rising atmospheric temperatures that we didn't see before. It is normal now to go way beyond 35 degrees in summer, all summer, in areas where 28 degrees meant that people were, going crazy with heat. So it's unprecedented, and it definitely needs to have an impact because most of the heat of the atmosphere goes into the ocean. So it doesn't come back up. So that's the right way to reason for searching for a tipping point, for instance.
Thank you for the talk. I have one question about the marine heat waves.
Yeah.
I guess that the easiest information, the most accessible information that we can get in the oceans is surface information, especially with the use of remote sensing data, big data, and so on. And you also showed us sea surface marine heat waves on surface. So my question is, since you're also a oceanographer and biochemist in specific, is it possible or are we already at this level, the level of combining sea surface information and the mechanisms within the marine system, the biological mechanisms, in order to have an idea what's happening within water column with marine heat waves?
Yeah, we do. I mean, we have automatic profilers that we can launch, and actually we do. We get them to do 5 or 6 profiles a day. And we did that for, it was another project, but we were measuring things with an atmospheric river, and there was this eclipse going on. So we said, hey, let's see if we can catch the variability of the sea. So yes, we can let them do their thing for a long time. The thing is that we cannot go down 100 meters, let's say, with some of them. And for that, you need Argo floats, that are very much linked to the open ocean. So it's a problem really to launch them in coastal ecosystem because they go away really easily. So you will have, a limited amount of time. We are now using gliders to do some circuits and get these info. But really, what works and has always worked is moorings. Moorings to the bottom and just have a fixed point. But the cost of doing so is huge. I mean, whoever has worked with the moorings in the sea knows that you need a lot of money, which led us to think that we can work with engineers to make our own buoys, in-house and lower the cost. And we are in the process of doing that. But really, automatization is key. The thing is that the physics goes, a lot faster than the chemistry and the biology. So right now we have automatic cytometers that do pictures of phytoplankton. We have some sensors for chemistry, but the frequency of the data acquisition is not nearly where we need it to be. So if there are technological people, watching this, get to the chemistry part of the automatization of data acquisition, because that's really what is needed now to level the playground.
Do we have more questions around? Okay, so then it's time for finishing. We have to evacuate Camila as soon as possible because she has to go to France. So we are going to have lunch now, but if you want to talk with her, should be right now before we leave, because we won't go to the kiosco. The kiosco is full of water and that. Okay, thank you very much, Camila, for coming, for sharing your time here, and thank you everyone for being here today.
Thank
Bye.
you very much.